again instead of online. So they will be in here at 5 o'clock to give teaching evaluations. So we don't get a quiz on Monday because apparently most professors have a problem with the students doing their teaching evaluations. I never seem to have that issue because I motivate the students to do the evaluations. All you need to do is have how many students did it. So, all right, so anyway, we won't have a quiz on Monday. Does that disappoint anybody? All right, any questions on the projects? You have to make everything. You're making everything you need for the fabrication, and if you've taken 421, so then you would know how to do the layout and how to do the chip, right? And so, well, if you don't, we're not going to do the layout. We're not going to do the chip. But in 421, you learned how to go from the transistor schematics to the actual physical implementation of the chip. So also, just before I mention it, or before I forget, so I spent about $60,000 within about a month ago to upgrade our Cadence servers so that they are like ridiculously powerful now. And then I also got the VPN and VNC working so that you can run Cadence just as fast at home as you can on campus. People that took 421 already, don't be hating me because of that, because you won't, if you haven't taken it, you'll understand how significant that is. Basically, you got to come to school to do everything, so now you won't. So we'll have some significant computing power and things that we can do. And I'm kind of a little worried because it's such a significant amount of computing power, the cluster that we have. I'm just thinking the computer science people are going to be looking at, because it's like 200,000 just in processors. So it's like a little supercomputer. All right, and Dr. Griggs got it all planned out. He's going to start doing the implementation in the summer. He said it should be done by mid to late May. It's going to be professional level, so redundancy and all kinds of things. So, all right, let's go talk about op amps. I want to go through some of the things in chapter 24. Specifically related to op amps, and I'm going to go through common mode rejection ratio and power supply rejection ratio in a moment, but I want to talk about biasing one more time and op amps and offset, okay? Because I want you to be able to answer these questions because I kind of alluded to them last time. But if you look at the basic op amp topology, this is the two-stage op amp in the beginning of chapter 24. And I want to try to describe this so that you can intuitively understand. So this is the two-stage op amp. This is the plus input. This is the minus input of the op amp. If I look at this and just to make sure we're totally clear, I don't want anybody not following. If you have this is V plus, this is V, this is minus, this is V minus, and this is V out. Everybody follow? Okay, so this rectangle here is what's in here, and I'm not showing the bias circuit at this point. I'm going to do a simple bias circuit for you. So we did all this fancy stuff with biasing, but you can do a bias circuit just like this with two MOSFETs or a resistor and a MOSFET. And then this is a current mirror right here, right? And then you make the long L so that it drops a large voltage of VDD and set the bias current in the op amp. So let me ask a simple question before we move on. Why Why, what's wrong with this and what's right with it? What's right with it? What is it? Simple. I don't have a lot of power burning in my bias circuit, right? So there may be times in industry where you're designing like a hearing aid amplifier and you want it to be super simple and low power, and now you're not biasing or burning anything and your battery voltage isn't going to change that much, right? Everybody follow that? So I can do this. What are the drawbacks though? If you're designing an op amp like we use in lab, where you're changing the power supply from, say, 5 to 15 volts, what would be the problem? Yeah, it's not stable. The current and the bias would vary all over, hugely with VDD, unlike the beta multiplier, which is independent of VDD. Everybody follow that? Okay, so I'm showing this, and I'm assuming we all know where this comes from, but I don't want, because we spent so much time on power supply and temperature stability and all that, I don't want you to lose sight of the fact that your projects and what you work on can have something as simple as this, if you feel it will work well. Okay? Now, what else is missing out of this block? Nothing. I could draw the ground connection and the power supply, and all these transistors would be inside the block, and I'm done. You all follow that? Now, I want to talk about offset voltage, and this is like something when you go for an analog design interview that they really talk a lot about. And I'm going to go through it in several steps. First, what I'm going to do, I'm going to come back to this one. I'm going to show you how you look at the offset voltage. And so what I'm going to do is I'm going to take a real op amp, and you could probably see this on your data sheets. And I'm going to put this, let's just put some numbers in, and plus 5 volts, and I'm going to make this 2.5 volts. And actually had a conversation about this yesterday with someone on a phone call. This is called the common mode voltage, and they didn't understand, and this was with regard to a certain circuit. And I tried to explain that when you have signals that go up and down like this, and you have one power supply voltage, you have to have the single swing around the common mode voltage. And then the question is why? Well, if you use ground, you ground this input. We already know there's problems with the input common mode range of the diff amp, right? So if I move this up, I'm in the common mode range of the diff amp. But if I'm using ground here, I can't ever go negative, can I? So I have to use a voltage and have all my signals referenced to the common mode voltage. Everybody follow that? So when I do mixed signal design, nowadays basically everything is single supply. I have to have some reference that the signals swing around. And this is often abbreviated as VCM, and it's also often just VDD over 2. Not always, but often. Does everybody follow that? Now, if I look at this op amp and I ask you, not precisely, but roundabout, what is the output swing here? Or what can the output swing go between here and the op amp? 0 and ground, VDD, right? So if VDD is 5, it could swing between 0 and 5. So now I'm going to plot. So this is something you should be able to do. I'm going to plot, I'm going to call this VP. I'm going to plot V out versus VP. And I'm going to put, let's say, this is 2.5 right here. And I ask you, sketch the output versus VP. You would do something like this. Because when VP, okay, you need to understand this. When VP gets above 2.5, the gain here, whatever the open loop gain is, times VP minus 2.5 goes to a positive value. That times the big gain causes the output to swing up to VDD. Does everybody follow? And when I'm below 2.5, this is a negative number, and that AOL times the negative number causes the output to go down to ground. Does that make sense? So now, over here, where VP is approximately 2.5, if you zoom in on your designs, when you do your projects, this slope will be equal to the open loop gain. And through the negative feedback, I always push VP to go back to V minus. So when I do my designs, actually I'm going to pause on this because I've had so many problems in the past with students not knowing how to do this. So let's pause, and I have and maybe I should actually show you with simulations instead of doing it this way. Students tend to like simulations. What do I know? All right, so let's go here. Let's go to chapter 24. Let's look at figure 24.3. This is an op amp. I've used Cascode current mirror, but this is the same stuff as what I just had, right? And here what I'm going to do, my power supply is 1, my start value is 0, so I'm going to go 1 volt. Now I'm going to make mistakes because this is stuff you guys waste like 4 or 5 hours all day on, all right? And I don't want you to waste time on this. So I'm going to do from 0 to 1 volt in 1 millivolt steps. Does that seem reasonable? Yes. All right. And I'm going to hit run. And then I look and I see I start at 0. I sweep my input from 1 volt. I look at my minus input. It's at VCM, which is half a volt when the power supply is 1 volt. And I look at my output and I say, hey, my output's swinging up just like he did in lecture from 0 to 1 volt. And that slope is my gain. And I take the derivative to find what the slope is, and I get a gain of about 50. And I'm like, crap, how am I going to meet the requirements of the project of 1,000 or 10,000? I don't even remember what the gain is right now. Tell me what mistake I made. Tell him, Jason.
This step is too small. 10 millivolts is too large.
Yeah, 10 millivolts. I'm going 4.95, 4.96, 4.97, and I'm going 10 millivolts at a time, right? So what's the distance between 2 points on the VP? 10 millivolts. So if I look at what the slope is that I can get from that, it's 1 over 10 millivolts. So at best I would get 100. You see what's happening? The way they took this, you see how the gain's only 50? So you're not going to, and I've had them where they've done something like this. This kills me because it actually took me like 15 minutes to figure out. They go, type of switch, no, they do, what was it? They did something like this. All right, and they did run, and they're like, I'm sweeping this, and I just can't get my output to change, and I don't know what's wrong. And I'm looking at them going, yeah, they're sweeping, I plotted the input, and I'm like, well, the input's sweeping. There's the input. It's going from 0 to 1. That's what it's supposed to do. And so if I ask, what's the difference between this plot and if I change the step to 1 millivolt? No difference. They look exactly the same, right? I can't tell the difference. It goes 0, 1 millivolt, 2 millivolts, 3 millivolts. But when you plot VP against itself, it's going to be a line that's straight, right, with a slope. So I sit there and I'm like, I don't know why your gain's not working. And I'm spending all this time looking at the biasing and trying to figure out what's going on. And then I finally look here and I go, what the hell? 1 volt increments. So it goes 0, 1. All right. So I'm going to put 1 millivolt, and then I'm going to say run, and I'm going to look at actually, let's do this, and then do that. And I look, and I see my gain's 440, and I go, okay, well, that's better, but what do I expect the maximum gain I could get then is? 1,000, okay, if I were hitting things perfectly. But if I'm trying to get 10,000, what kind of step do I need? I need like a few hundredths of a millivolt, right? So I get real step, and then I need to limit the range. So let me do it right. Let's go over here and go 4.95, or whoops, 495 millivolts to, and that's probably even too much, to, let's go 8 to 502 millivolts, and then let's put a 1 microvolt step. Does that sound good, Juan? Where's Juan? All right, we miss you, Juan. All right. So he was here earlier? All right, so there you see. And now the other thing is, op amps aren't magic. You just have a real high gain amplifier. We'll talk about stability, but you see how the output's actually changing, and now I'm getting up above 1,000. Any questions on this?
Why is the output of the derivative not? It looks funny.
It's not perfect because the devices are non-linear and you've got all of them going together. So the fact that you have gain, high gain, when you use the negative feedback, it's always going to go to the highest gain point, which if I look is roughly in this area right here. So there's like a teeny little, which I'm going to go over right now, a teeny little bit of offset depending on where it is. But you see, when I have a gain of about 1,000, it could be 499.8, 501, 500.1. You don't have enough gain to precisely control it and pull it into perfectly the common mode, perfectly 500. You're in this range, and that's where things are going to be happy. So if you want more precision, what do you have to do? Or more control? You need more gain. If you have more gain, then it becomes harder to make it stable, which again, we're going to talk about. So everybody understands how to do a DC sweep of the open loop gain of your op amp. Okay, so now that we know that, we're going to go back to offset. And before I cover offset, I'm going to show you how it's modeled in case you've forgotten, and we're going to do an example of it in the with a real circuit. So let's go to here. And the way you model offset is you put a small voltage in series with the non-inverting input. Does it have to be in series with the non-inverting? No, it could be in series with the inverting. This is a model. It's not really there, and I'm going to show you why. I can remember back like 20 years ago, the way you, let me just tell you a quick story. So the way you measure offset is that you plot an offset noise. If you take advanced analog this fall, offset noise are similar. Offset is noise at DC, but you do what's called input referred noise or input referred offset. And the way you measure offset is by looking at the curve. So here I'm going to show the slope. And let's just say VCM was here. And then ideally, it should be the curve, the output, V out, should be shifted to the right, right? But it's offset from where it should be. And I'm going to call this VOS. Everybody follow that? So I need to shift it this way. So I need to add a value here. And this can be positive or negative depending on what it is. I need to add a value to VP to shift it to where it's supposed to be. Does everybody follow that? So the way you measure offset, the noise, is you measure what it is on the output, you divide by the gain, and then you refer it back to the input. All right, and so the simple way to do this is to put the op amp in a follower like this. And then what should the output be? Yeah, but this is, if I put this as VCM, and then I measure the voltage here, this is the offset voltage I'm measuring. Let me prove that to you before we do an example, all right? So I just said we model it this way. So let's put, and let's just say that I ground this and the op amp can work with ground. Everybody agree with that? And what was the name of this topology that gives me nightmares when I say just put it in a follower and the student goes, what's that? So what is this? No. Voltage follower. Right? The narrative is so good, DS. All right, what is this voltage here then? Yeah, this is modeling with my op amp. It's not really there, but I'm adding it when I do my analysis. Okay, if that's the case, and I'm not worrying about the gain, what's this voltage? Let's just say AOL goes to infinity. Well, if that's the case, V out equals V out minus VOS times AOL. But AOL goes to infinity, and then that can only be bounded when V out goes to VOS. We all follow that? Okay, you agree that, here, let me write it, I'm getting, V out is equal to AOL times V plus minus V minus. And you would agree that V plus is VOS. And again, I put plus or minus because V offset can be positive, it can be negative. I'm going to prove this to you in a moment. Right? And then that's minus the minus terminal, which is tied to V out. So if AOL goes to infinity, remember when you did ideal op amps? Said, oh, the gain's infinite. What does that mean the output has to go to? This is going to stay bounded. What does V out have to go to? Don't all scream it at once. No! VOS. Because then I get VOS minus VOS goes towards, and then this stays. Does this confuse anybody? Didn't you do this in like Calc 1 100,000 times? Stuff like this where you take the limit. What? Come on. Killing me. Okay. So let's do an example. Are there any questions before I want you to understand offset. So let's do it with an offset. Let's do this amplifier. Let's analyze this amplifier right here. And let's assume infinite gain. What? How did that? What? All right, whatever. That's okay. The first 2 times I tried to run it today, it just gave me the black screen of death. Okay, so let's analyze this circuit with offset. Let's do it without, oops, I gotta modify this. All right, and I'm gonna do this the long way because I don't want to do it assuming the 2 inputs, but let's say they're not. So let's call this terminal VM. And then tell me how to analyze this circuit without assuming infinite gain. This current is, see, this is when I do it, it looks easy. All right? Well, you tell me. V out minus VM over 99K equals? We all agree with that? And then I'm going to go solve for VM. Yeah, I'm going to put, this is V out minus VM equals 99 times VM minus 2.5. Does anybody agree with that? Okay, so I'm going to move this over and write V out What's that? V out plus 99 times 2.5 equals 100 Vm. Does anybody agree with that? And then I can write V out equals AOL times 2.5 minus Vm, which is V out over 100 minus 99.25 over 100. And this, of course, is, does anybody agree with that? Did I make a mistake? Oh, sorry. 99 times 2.5. How's that? Roughly 25, but let's not be imprecise yet. Oh. I was seeing 2.5 there. All right. So if AOL goes to infinity, wouldn't you agree these have to go to, this has to go to 0? Would you all agree with that? And let me just, instead of wasting trees, then this has to go to 0. And if that has to go to 0, then I can write 0 equals 2.5 minus V out over 100 minus 99 times 2.5 over 100. Looking good? And let me see, that gives me V out equals 2.5 minus 99.2, 2.5 times, and this is times 100. And so let me factor out the be 2.5 times 100 minus 99, or 2.5. Anybody agree with that? Anybody follow that? So anyway, this is 2.5, this is 2.5, this is 2.5. Yay or nay? All right, Nick says yay. All right. So let's do the circuit now with an offset. So I guess would everybody agree that just to simplify things and use superpositions, I could drive this to 0, and now this goes to 0, and then do the analysis without the voltage sources in there using superposition and just the offset? Let me ask anybody that took circuits 1 with me, do you agree that you could get rid of the voltage sources? You better say yes. All right, so this is VOS. I gotta have my fun. All right, and so then what is now the output? Which is one of the topologies? What's topology is this one? Non-inverting. What's the gain equation? Tell me from circuits 1. So if my offset were 10 millivolts and at a gain of 100, then V out would be equal to 1 volt. Does everybody see the problem? This is a huge practical problem. Now, of course, you could AC couple to get the signal out. Okay, so I think we've covered the basics, why offset's important, what offset looks like. Now I want to go through back to this circuit. And I want to talk about the how I can make an offset accidentally. Okay? So here's what I'm going to do. Let's say there's 20, let's use the book process. There's 20 microamps there, 10 microamps there, 10 microamps there, 10 microamps there, 10 microamps there. The sizes. And then I use the op amp and I go, as I just saw, and I don't have any significant offset. But say, for whatever reason, you change this to a times 100 device. So then this goes to what? If this is, instead of 30 by 2, it's a 3,000 by 2, if I did the math right in my head. So this wants to go to what? 1 milliamp. Everybody agree with that? But wait a sec. I got 10 microamps here. So what's going to happen? When I put the op amp in the feedback configuration, this node has to go up, which causes this node to do what? Whoops, I did it the wrong way. This node needs to go down, which causes this node to go up. Why did this node have to go up? To shut off that PMOS. Because if I drive this node up, the PMOS shuts off. So if I had 2.5 volts here, I'd have, say, 2.45 volts here to make this node go up so that this current decreased down to 10 microamps. So when I look at the offset, I've got a 50 millivolt, what's called systematic offset, because I've got biasing issues. Now, I might want to do that because I need this to supply a lot of current. One example of where a circuit like this might be used is if you're supplying power. So you got your input as a band gap and your output is a feedback through a resistive network, and this supplies power to a portion of the chip. All right, and so you want this big to supply the power, but it results in an inherent offset. Does everybody follow that? So let's go show that in the simulations. Let's go show the offset. Let's go back to that schematic, the 24.3. And let's go here to this device, and let's give it an M of 1. Oh, wait, before we do that, let's look at it. Make sure I didn't mess something up. And we see the gain's about 1,000. We see there's relatively no offset. How can you tell that? Well, because when the VP starts to switch around 500, this is where VM is. We can actually plot that. Whoops. You see that the gain is high. So there's really not any offset there because we know what we're doing with the biasing. So now I'm going to go over here and I'm going to change this, and I'm going to put M devices in parallel, 100 in parallel, and actually, oh, they're showing up. And so now this wants to source a milliamp of current. But of course it can't because it's got a current source down here that only wants to sink 10 microamps. So we're going to see this node go up, and we're going to see VP go down in order to shut this off so that the current's balanced. So watch this shift. Now, what do you think might happen if I introduce too large of an offset? What's the maximum offset I can show on this plot? Well, 5 millivolts. How do I know 5 millivolts? Because I'm starting my sim at 495. So if I see a straight line, I know my offset's greater than 5 millivolts. So I'm going to hit run. See, you guys have to design your op amps to drive like a kiloohm, right? So you have to have some DC current, and you may decide for efficiency's sake to make this bigger so it can supply the DC current when it needs to. Now it results in a systematic offset. What are random offsets? Those are when the transistors don't match each other. They don't have exactly the same characteristics. All right. So systematic offset is when you've designed your transistor so you build in an offset. Sometimes you want that. Okay, so I'll hit run, and let's see what happens. And I see VM there at 0.5 volt, and I see V out staying up at 1 volt. I'm not even showing when it switches. So why don't I go back? Does everybody follow that? Or does anybody follow that? So I'm going to go back here, and I'm going to change this to, how about 450 millivolts, which I know is enough, to 550 just to have, whoops, 450 to 550. Then I'm going to hit OK and run. And I'm going to look, and I say, holy crap, my gain's only going up to 360 because I've got this offset, which is about negative, well, it depends on which way you put the plus and minus, negative 15 or 14 millivolts. Does everybody see that? So what do you think is going to happen if I go back here and I change this to 10? Just tell me intuitively what's going to happen to the curve. It's going to shift to the right. Boom. What do you think is going to happen if I change this to not have any multiplier, but I use a smaller width? It's going to move the other direction because I got to yank this node down in order to supply the current that I want to supply here. So I hit run, and it's going to move the other direction. Okay. I really want you to understand this offset and how I'm making it in there and how it's going in. And then now, if I ask you, okay, well, you got a 10 millivolt offset, what are the two inputs of the op amp? What are the voltages going to be? One's held at 0.5 volt, right? This one's held at 0.5 volt. The other one is going to be, in this case, at 510. Well, wait, they're not at the same voltage. It's not magic. You've designed it so that the op amp has an offset, so you expect them to be different. And when you look at a data sheet for an op amp, you will see the offset. Any questions about this?
Now, what part of being able to do that just so we can drive resistive load?
You might want to be able to drive a resistive load. You might want an offset between the two for whatever reason. Yeah, I mean, you need to know what offset is. I mean, people are going to ask you, if you go for an analog design job interview, they're going to ask me, what's offset and why is offset important? Give me an example. Well, okay, here's offset. It means that when you plot the curves and you plot V out versus VM, that where the high gain region is shifted, left or right. Why is it important? Well, if you have a high gain circuit, for example, this follower or this non-inverting op amp, the offset's multiplied by the high gain and it shows up as a DC on the output of the op amp. So you got, well, why would that be important? Well, if I have a gain of 100 and my offset's 10 millivolts, I get a volt on the output of the op amp. So now instead of my output of my op amp being able to swing the power supply range 0 to 5 volts, I'm only able to swing a swing of 4 volts because I've lost a volt due to the offset. Everybody follow that. I want you to be able to answer those questions. All right, so I'm going to stop and, well, before I stop, let's go back to the original schematic and let's talk briefly about mismatch. So I could model a mismatch with a voltage source in series with one of these, or I could model it with a different width. And now if I hit run, you see I've got a little bit of a mismatch. And if you look at the curves, and let's go back to what we had where this was 4.95 and 5.05. And I hit run. And I see what, but just because that minor mismatch in the widths, what's happened to the offset? You get a shift in the offset. Is this making sense? Do op amps seem magic? No, they're not magic. All right, I don't want you to take this class and go, well, I didn't learn anything. I don't even know how an op amp works. That would be like, not good. All right, I want to talk about common mode rejection ratio and power supply rejection ratio. Okay, because those are requirements in your projects. So let's do that. And so common mode rejection ratio we don't need to save that. Is anybody still using the videos? I agree. All right. Common mode rejection ratio is what's defined as the difference mode gain over the common mode gain. So refresh my memory for a diff amp. What is the difference mode gain? That we derived last time, and maybe the time before that, and the time before that. Anybody agree with that? And then my AC, I need to show how to derive. It would be a good to have a quiz today on how to derive the gain of a diff amp, wouldn't it? I told you last time, I'm like, you need to know this and you need to be able to drive, and I've derived it like 4 times. I mean, I know what some of you are thinking. He's getting paid for doing the same thing over and over again. So I want high common mode rejection ratio, which means I want to amplify the difference. I want high difference mode gain and reject the common mode signal. So here's how we're going to do it. I'm going to take the difference amplifier, my diff amp. I'm going to come down here and I'm going to tie the 2 inputs together to a common mode AC signal and then to some common mode voltage. What is this for, the VCM here? Well, it's not the offset. You're scaring me there. That's to ensure that the diff amp's on. You got to bias it up, right? It's the input common mode range. You got to ensure that the input's above a certain value. Okay? And a common mode might be like from the 60 hertz noise that I have on the power supply. That's the signal I don't want to amplify that's coming common. So a simple example of that, you know, Ethernet cable like up here, that has differential signals. PCIe bus, differential signals. USB 3, differential signals. The reason they do that is because you can go into a diff amp, and if your big wire is sitting in the wall and acts like a big antenna and you pick up this signal, you get this common mode signal on both wires. When you get to the diff amp, it says, hey, I don't want you, and throws it away. And then all that's left is this little differential signal that you have for your USB or your Ethernet or whatever. All right? So this is a big deal. Being able to reject the common mode signal that you pick up. All right? Nowadays, there's no high-speed transmission that I know of that's single-ended, one signal. It's all differential pair. Because one goes up, one goes down, and you get something that moves the signals up or moves them down. It doesn't matter. It's subtracted out with the diff amp. Okay, so here we go. I'm going to remove, and I'm going to put the current source I'm going to just call R out. Just call R out of the current source. And you know, you get different values if you use a cascode versus a regular. And I'm going to come over here and I'm going to call this V common mode, or V out common, and this I'll call V common, and then I'm going to define AC is equal to V out common over VC. And just as a sanity check for myself, and please don't make me cry, what do I want the common mode gain to be? I'm looking for something super simple. Big, small, medium. Small. I want it to be 0. I don't want any common mode signal to get to the output of my diff amp. Okay, I want it to be 0, so I want V out C to be a rock steady DC voltage. All right, so here we go. Next quiz. Oh, wait, we can't have it on the next quiz. What's happening next time? At 5 o'clock?
Oh, yeah.
What's the AC voltage here? What's the AC voltage here? And then what is the voltage here between the gate and source called? Do I need to label VGS1 and VGS2? Nope, they're the same. They're physically tied together. They gotta be the same. I'm gonna call this current ID, AC, and this current ID. And what is that current? See how easy analog is? Now what's the current flowing down there? All right. And then I look here and I say, what's the current flowing in there? And what's the current flowing in there by the current mirror action? Wait a sec. So if I've got ID flowing in there, which equals that, and I've got the ID here and the ID here, these are equal. So, but I know that this is VSG, and the ID is equal to GMP times VSG. So, won't because of symmetry, don't these have the same VSGs? Don't they have the same IDs? So doesn't that mean they have to have the same VSDs, or in this case, the same VSD is the same as VSG? So won't that be equal to minus VSG? So this is AC ground. And so this node right here would be 0 minus VSG, or minus VSG. This would be 0 minus VSG, or minus VSG. Everybody see that because of the symmetry? And then that's equal to minus ID all over GMP. Anybody agree with that? All right, so now I need to figure out what the VC and VGS and all that is, right? So I'm going to write, let's see if I can get away with this. VOC equals minus ID over GMP. VC equals ID over GM N plus 2ID times R out. Anybody agree with that? VC equals the VGS, which is the ID over GMN, plus 2ID times R out. Currents cancel. And I get on the next page, dun, dun, dun. Everybody excited for lab tonight? You killing me? Can we go home? They closed donuts? Oh, they did? What kind of desperate person breaks into a donut shop? Homer Simpson? Seriously. All right, that's what I have. You know, is anybody familiar with, you know, when you own a bakery? Not that I know anything about bakeries. But you have to start work really early in the morning, right? Like 2 in the morning. So when are they breaking in? Like those few little hours between when someone's there and they close? That's not good. People don't like to buy stale baked goods. They like fresh baked goods. What'd you learn? Bakery stuff. All right, tell me how I can simplify this. Would everybody agree with that? Well, what did I say approximately? Why did I do that?
Because GMR
GMN, 1 over GMN, if I've got good open circuit gain, remember the first few weeks, is going to be really small compared to R out. Right? Isn't that a reasonable assumption? Well, yeah, if you just have a simple current mirror, it would be mega ohms. But if you go with cascode, what happens? Gets to giga ohms. You have real high gain, it gets to giga ohms, then what happens to your common mode gain? Gets really small. If you put a cascode current source there for your tail current, it'll get really small. I'm going to modify that in 2 seconds. All right? So then I can write my common mode rejection ratio is equal, and it's generally in log, of the absolute value of GMN times R out N in parallel with R out P all over 1 over GMP times 2R out. And if you look at this, this means to maximize breaking into a donut shop. I thought they were just tired of making donuts for college kids. I didn't. Damn healthy college kids always wanting those crazy donuts. Yeah, I'm getting to the point when I travel and they say, "What would you like?" I don't want to offend anybody, but I was like, I want to make sure there's lots of meat in my lunch. I need meat. And they're like, because everybody's like, I'm vegan or I'm vegetarian or whatever. And I'm like, I need meat. I'll be hungry in like an hour. What's that?
Right, yeah. What's the most unhealthy food? See, just wait for the gas. I'm just kidding, I'm gonna die.
All right. So let's go back and talk about that for a second. Okay, so if you look at real op amps, I remember back in like 87 or so, I went to, actually it was at, what's that casino there on Charleston? Or is it Sahara, the station one? No, it's like Palace Station. Is that, what's that on? That's on Sahara. I went to a conference there in Sahara on noise reduction. And I was talking to the engineer there, and he was talking about how this was still board design with op amps was still real common. Now it's chips, but it's basically the same thing. He was talking about how hard it is to get good common mode rejection above 100 kilohertz or so. So why, given what I've said already in class, why would that be a concern to you? If you're transmitting high-speed data, who transmits kilohertz data for high speed? Nobody, right? They're doing gigahertz and megahertz. So you want common mode rejection at high frequencies. Okay, so here's the problem. So I decide I want good common mode rejection, so I do the following. I put a cascode down there. I say, I'm going to live with the reduction in input common mode range and just design with a really small overdrive. So I do this, and then I do my CMMR I do my calculations, I get a value, then I simulate it, and I look at the CMMR. There's examples in the chapter 24, and I see this, and then I see, hey, 10 kilohertz or something, the CMRR starts to roll off. And you're like, oh, that's not very useful. I want it to be high. Well, here's the problem. When you do real design, and you have this, there's a capacitance here as well. So when you do the layout, you need to minimize the capacitance on this node. So if there's a capacitance there, what happens as you start to go up in frequency? This impedance starts to become much, much less than the output resistance, R out, of the tail current source. Everybody follow that? And so it starts to dominate. So even though you used cascode there and you got giga ohms, It doesn't take much of a frequency at all, even with a tiny capacitor there, to get a capacitive impedance less than gigaohms. So it causes the common mode rejection ratio to roll off. Everybody follow that? Any questions? You're going to minimize the area on the sources and try to use high. Now, in reality, what they will do for like Ethernet, they will put some inductances in here to try to resonate with the capacitances to increase the common mode rejection. So for the inductance doesn't do much at low frequencies for anything, but at high frequencies, that inductance, it depends where they put it, can resonate and increase the common mode rejection ratio. But if you put it in series like I've drawn right there, it also reduces the common mode or the difference mode gain. And just to refresh my memory, what was the difference mode gain? Yeah, it's the normal one we talk about where you're amplifying the difference. So I have to be careful how I do that, but they try to match the capacitance to boost the impedance. And refresh my memory, if I have a capacitance like this, and I want to see an impedance looking in there that's high, how would I use an inductor to try to make it so the impedance is high? Yeah, I'd put it in parallel. And then if I didn't want to mess up the DC, I'd have to use a big capacitor here. And then at certain frequencies, the inductive energy would transfer over, and I would see a Z that goes up. And at higher frequencies, then the inductor's then open, and then you're left with the capacitor rolling things off. Okay, I really want to talk brief. Are there any questions about this? I wanted to cover one more topic really quick, and we can pick this up on Monday, which is power supply rejection ratio. But are there any questions on common mode rejection ratio? Question? All right, so I'm going to go back to my basic op amp. And I'm going to talk about this, and I'm going to try to talk about it, and I'll bring more discussion next time. But real quick, before I do that, if you look at here, when you're doing your projects, here's a simulation of common mode rejection. You see how in the top schematic, I'm applying a DC, I'm applying a AC signal. Crap, and that's one thing I should comment on too. You see the 100 meg resistor there? When you do your op amp designs and you want to look at the open loop response, not with feedback or anything, because with feedback, the gains go down, right? If you use a follower, the gain goes to 1. What we will do in the designs is we will do something like this, where we have the following. So I'm not going to show the AC right off the bat. I'm going to put, let's just put for your designs 1 volt, but it has to work at other voltages, of course. So this would be plus and minus. Now the question is, we know we have an offset. Could be 1/10 of a millivolt, but if I have 1/10 of a millivolt and a gain of 10,000, it gives me an output of 1 volt and things don't bias up correctly. So how do I get the op amp to bias up correctly? The answer is I put a DC stability circuit in there, and you're all going to use these. And that is the following. So for DC, what is the output voltage? So for DC, what is the impedance of the capacitor? Open. So doesn't the output come directly back here? So wouldn't the output have to be 1 volt or the common mode voltage, because we want our op amp to be going up or down? Everybody follow that? Now, if I had like 100 meg here and a 10 microfarad capacitor, what is tau? Right? So if I go look at this and I say I'm going to put an AC signal in here, won't, for all intents and purposes, even down to a hertz or 1 cycle per second, won't this output for the simulation show the AOL? Or won't it show the gain that goes through, the open loop gain? So let me make sure you follow. For AC, what is this voltage? 0. For AC, what is this voltage? We'll call it Vin. Vin. So for AC, down to a hertz, because I got a time constant of 1,000, what's this voltage? The gain of the amplifier times Vin, and that's the V out. Because I have no feedback. Does everybody see that? So if I want to find the AC gain of the amplifier, going back, does everybody understand why I need this? Sets a stable DC operating point. So if I go back now and I look at this, this is going to give me my difference mode gain because I got DC bias. I apply 1 volt AC because I know AC doesn't care about the actual amplitudes. So I get 1 volt there, so I get a value of AD right there. Now over here, I got to worry about, are there any questions on this one to get the differential gain of, or the open loop gain of the op amp? So over here, I still have an offset, so I have my resistor and my capacitor to get the 2 voltages equal. This is still at, let me highlight it. Let's do it here. This is still at, yeah, come on. Oh, you're killing me. This is still at AC of 1 volt and DC of 500 millivolts. So I put the resistor capacitor in, but now I'm applying the same signal to both for AC to both gates. So I get a common mode signal. So if I do that, I get my common mode output gain here. So let's run this, and I won't talk about power supply rejection until next time. And let's plot the difference gain, and I see I've got about, what is that, 300 or something like that. All right, everybody see that? Now let's look at the common mode gain, and you see it start to roll off at 10 kilohertz. Let's look at the common mode gain. And I see that at low frequencies, I have a gain of about, what is that? 2 would be 6 dB, so slightly above 2. And then at 10 kilohertz, I start to roll off. And so when I do the ratio, I'm going to get my common mode rejection ratio. But you see how the AC gain, you know, I could talk about this stuff all day. But we showed the gain of this would be less than 1, right? Didn't we show that? Remember, I derived that right here. Yeah, I hate it when professors can't shut up. But we need to do our quiz, and I want to keep you late. So everybody, oops, that's not the right one. Everybody says, this is going to be less than 1, right? I mean, this will be less than 1. It's 1 over GM times 2R. It's going to be like 0.03. Does everybody see that? So how in the world could I get, in my simulation, the gain here being 2, or slightly above 2? No, go look. If this gain from, let's say I have 1 volt here, and let's say here I have 10 millivolts. So the gain's 1/100th. Well, if I have a gain of 10 millivolts and I go through this amplifier with a gain of 300, what's the output? 3. Does everybody see that? Now it turns out in both of these that this output stage gain subtracts out and you only care about the diff amp, but that's why the gain's not so low. All right, let's do the quiz.